In this video, we want to describe the basic principles that lie behind circular motion. We want to explain exactly what it means by circular motion. So when you talk about motion, you're talking about an object that is moving. So motion is the word movement. The meaning of the word motion is movement. So we want to explore different kind of things in here. We want to look at different kind of motions. We want to look at different kind of forces and the formulas that we're supposed to use for objects that are moving in a circular position. So let me give an example. You might have a circle, all right? You might have a circle. And I want you to understand that in this circle, you have the center of the circle. And an object that moves from the center, a line that moves from the center of the circle, touching the circumference of the circle, is called the radius. If the other part also moves from the center of the circle, touching the circumference of the other circle, that is the radius. And when you combine the radius, which is the r, plus the r, it's going to give us 2r. And that 2r is the diameter, meaning that this is a line that moves through the center of the circle, joining the circumference of one circle to the circumference of the next circle. So now, what are some of the things I want us to get from this introduction to circular motion? I want us to understand that we have objects that can move in a linear position. And when I use the word linear, I mean objects that are moving in a straight line. When I use the word circular, I mean objects that are moving in a circle like the one I've given here. So you might have objects that are moving in this particular position. So now, I want us to relate the linear motion that you've learned to the circular motion. And I'm going to use certain words to distinguish exactly what we mean by circular motion and what we mean by linear motion. Okay? Now, back then we learned about the word perimeter. We said this is the total distance around a shape. This shape can be anything. It could be a triangle, it could be a rectangle, it could be a circle. A circle is also a shape. So now, if you remember the formula for perimeter, we talked of it as distance around a shape. Okay? So now, if we say, all right, we say perimeter, we're talking about perimeter here being equal to total distance around the shape. And when it comes to a circle, when you're defining perimeter, you say this is equal to 2 pi r. Okay? And that is the formula that we used to use to define the perimeter of a circle. All right, and that's the formula that we used to use when you're trying to find out what is the total length or distance around that circle. Okay, the other thing I want us to understand from here is that when you're talking about circular motion, all right, and you have been taught to find that distance, it doesn't now become linear distance or just any displacement. We talk about it as angular displacement. Okay, so there's really a fine distinction between the word linear and the word angular. When you're using the word angular, anything that you're using the word angular with, it is in relation to objects that are moving in a circular position. Anything that you're using the word linear with is anything that is moving in a straight line. All right, so now this could be circular position. Okay, so now for formulas that move in a circular position, you're going to have S here representing, this S is not a 5, that's a S. This S is representing the displacement, which can be equal to pi r. Okay, and the pi r, not the pi r, but theta multiplied by what? By r, meaning that the r is standing for the radius and then the theta there is the angle. Okay, so what we're doing here is that the S there is now giving us what we're calling displacement under circular motion. Okay, that is displacement under circular motion. So given the linear velocity, given the linear displacement, we can find out the value of the theta. We can also find out the value of the radius. Okay, so I want you to take note of the first formula here, and this formula is the one that is describing what we're calling linear displacement. Okay, we're talking of it as linear displacement. All right, so now this linear displacement we're talking about, so let me just label it linear displacement. Linear displacement is the formula we use. So meaning that if you have been given the distance or the displacement of an object which has traveled a certain kilometer or a certain length, we use s. S is symbolizing that displacement. Then the theta there is describing that that angle there. Then the r is the radius. Okay. So now the other thing we can talk about here is the angular displacement. Okay. The angular displacement is given by what? So we are talking about the word linear, moving in a straight line. So when it comes to a circle, we use, to describe that displacement of the distance traveled, we use theta. Okay, and theta is equal to 2 pi r. Okay, what we're calling this is angular displacement. So now the word angular comes in because we're talking about a circle. So there is now angular displacement. Yes, angular displacement. Okay, so this is just the first formula we've talked about. Formula 1. This is formula 2. All right, let's look at other formulas. Formula 3, what are we going to look at? Under formula 3, we can have velocity. And when you are defining this velocity, we say this is the rate change of displacement with respect to time. So meaning that when you are describing velocity under linear positions, all right, this is angular displacement. So when you're talking of velocity with respect to linear, so I'll put the word linear here. Okay, I'll put linear for 3. This is just not any velocity, this is linear velocity. So under linear velocity, what we are saying here is that when you define velocity, we say this is the rate change of displacement with respect to time. Meaning that the velocity now is equal to the rate change of that displacement. That displacement is linear displacement, which is symbolized by the s. But there's a change in s with respect to what? To time. All right, this is in form of the linear velocity. But when we're describing an object that is moving in a circular position, and then you want to find out what this velocity is, we call it angular velocity. All right, so we call that angular velocity. So I'll just relate this with that. Down here I'll note that under angular velocity, the symbol that we use to describe angular velocity is not v, it is omega, which is this. Okay, and we said that if this is now talking about the linear distance, if this change in s is talking about the linear displacement in relation to the angular displacement, we're talking about theta. So it is going to be now change in theta with respect to time, and time is a quantity that never changes. So that is the t. So when you're describing this, this is now called the angular velocity. This is angular velocity. Perfect. There we go. What other things are we going to talk about here? We're going to talk about acceleration. Acceleration, when it comes to the linear acceleration that we know, the formula is this. We know that acceleration is given by the final velocity minus the initial velocity over the time. Okay, or v2 minus v1 divided by time. That is what we're calling linear acceleration. So with respect to objects that are moving in a circular position, we're going to describe it in terms of angular. So that angular acceleration is now referred using alpha. Okay, and it is given by velocity. So velocity that we're talking about here, since it's angular velocity, is going to be omega final minus omega initial divide the time. So these are the formulas that we're going to use. So now let me label them now here. So now the formula we're going to use under objects that are moving in a circular position when you're finding the acceleration, which is called the angular acceleration, is this one here, given by acceleration being equal to the final angular velocity minus the initial angular velocity. You divide that by time. The other formulas, I'm going to label this as formula 4. Okay, the other ones that we're going to use here is when you're finding the velocity, which is angular velocity, which is going to be equal to the change in theta divided by time. And then when you're trying to relate that with the linear velocities, you're going to have change in linear displacement with respect to time. And then you're going to find out that angular displacement is theta being equal to 2 pi. So this is how you're supposed to make a clear and fine distinction between the objects that move in a straight line and objects that move in a circular position. So now, the other formulas that I want us to know here. So there's this formula here which says linear velocity, which is v, can be equal to the radius multiplied by the angular velocity. So this formula here can now relate the angular velocity to the velocity, which is the linear velocity. So you might be given the angular velocity, which is this one here, and you might be given the radius. Then you're told to find the linear velocity. Or you might not be given the final velocity or the angular velocity, you've been taught to find the angular velocity, but you don't have but you have been given the linear velocity and you've been given the radius. So you can make this the subject to the formula to find out what that value is. So the purpose of these formulas is just to relate linear velocity to angular velocity. There's another one which can relate linear acceleration to angular acceleration. Which one is that? You're just going to say acceleration is going to be equal to the radius multiplied by the angular acceleration. So for this one also, it is all the same. You can relate the formulas and see how you can distinguish linear acceleration to angular acceleration. So this is, I only put up 4 formulas there on top. So this becomes the fifth one, and this becomes the formula number 6. So there are other formulas that you can manipulate. For example, there are other formulas of motion. For example, you have the final velocity being equal to initial plus AAT. For objects moving in a circular position, the velocity is the angular velocity, which is the final angular velocity, equal to the initial angular velocity, okay, plus the acceleration becomes now the angular acceleration times a quantity that never changes. You might have v squared equal to v squared plus 2ax. All right, so now manipulating this now to objects that are moving in a circular position, it becomes the final velocity here becomes the angular velocity final squared equal to the initial angular velocity final initial squared plus the 2. Then the a there we have the acceleration, which is in linear acceleration, but for objects moving in a circular position, what we have? Angular acceleration, which is referred using pi. Then the s there is the distance traveled, but in relation to objects moving in a circular position, the distance is theta. So any equations that you know under linear motion can be manipulated. The only difference is in the change of the speed, the acceleration, and as well as the distance. The distance under linear motion is called the linear displacement. When it comes to objects moving in a circular position, we use theta to describe that distance. Well, then what are the SI units for these? Okay, what are the SI units? I want us to walk away with very important lessons from here. When you mean the SI units, it is important to know that with respect to the SI units, we're going to have the angular velocity, so under angular velocity, we're going to have rad per second, because what we have on top of the angular velocity, when you get back to the formula of the angular velocity, we said it is a change in theta divided the time. So the theta is in rad, the time is in seconds. All right, which other thing? Angular displacement. Angular displacement becomes, it is always measured in rad or radians. Okay, we're just talking about the distance of an object moving in a circular position, that is in radian. Okay, and then the angular acceleration, just like the way you have it meters per second squared. But for the angular acceleration under objects moving in a straight line, remember the meters now change to the radians, so it becomes radian per second squared. So these are the SI units that you're supposed to look for when you're finding objects moving in circular position. So you can also convert these objects into certain parts. Okay, you can do the conversion factors, because you know that one rad, okay, or a pi is equal to 180 degrees. So you can convert the degrees into the radians. For example, given 120 degrees here, then you've been told to convert these 120 degrees to radians. That is what you do. You find out the value of y here by cross multiplying. You might not be given that, because a pi is 180 degrees. You might be given revolutions. A complete revolution is one rev. A complete revolution like a circle is 360 degrees. Okay, meaning that one rev can also connect with 2 pi, because 2 pi here, the pi is 108 by 2 is 360, giving us that. So if I want to convert the revolutions to radian, I can use this conversion factor here. There we go. But if I want to convert the number of revolutions to degrees, I can use the above conversion factor. So if I want to convert the degrees to radians, or convert these revolutions to 360 degrees, these are the conversion factors that you're supposed to use in this particular kind of a topic. So thank you so much for paying attention, and looking forward to having you in the next session.